Okay. All right, so it's a great pleasure of Sahan Seifnashri from the IS. He'll talk about non-invertible QCAs. Please take it away.
Yeah. Hello, everyone. Thank you very much, Sakura, and organizer, for inviting me to speak at this wonderful online seminar. So today I will talk about a work in progress with Shuheng, which has been going on for more than a year now, and we hope that we at least put the first paper on the archive soon. And I don't have to say that. Please feel free to interrupt me if something was not clear. Okay, so I'll talk about non-invertible quantum cellular automata. And another title for this talk would be how to define non-invertible symmetries on the lattice. Okay, so to start, let me first review how we think about ordinary invertible symmetries on the lattice. So an ordinary invertible symmetry on the lattice, we define it as a unitary operator U that commutes with the Hamiltonian. So if this were quantum mechanics, this would be the end of story, and we would say all symmetries just correspond to unitary commuting with Hamiltonian. But if you have also spatial dimensions and there is a notion of locality, it's really crucial to also assume that the unitary operator maps local operator to local operator. It acts locally. So meaning that if you have an operator O, which has support on some number of lattice sites, then after acting with the symmetry, it only becomes slightly larger with some distance L, where this L is independent of the operator O and is independent of the system size. And that would be called the range of this symmetry. And that's how we define the notion of the symmetry acting locally. There is also, so I should say that this definition doesn't capture the most general crystalline symmetry, such as reflection or rotation. And then you have to use this definition. But for the sake of this talk, I'm not going to be worried about this distinction. It would be easy and straightforward to extend it to include such symmetries. And as I said, the locality condition is really important. And so, for example, it's important to discuss consequences of symmetry and most importantly, to do anomaly analysis. So importantly, to discussing anomalies on the lattice, all you have to assume is locality condition. And I should say that such a unitary operators are usually referred to as QCA or quantum cellular automata in the literature of range L, this distance L, and where L equals 0 correspond to on-site symmetries. Another comment is that in the infinite volume limit, where you don't have any Hilbert space, there is no really a unitary operator, but then instead QCAs are defined as some locality preserving automorphism. So you just define them by the action on the algebra of local operator. So A is the algebra of local operators where they act locally. So this is a definition for ordinary symmetries and its connection to QCA. Any question about these slides or terminology, anything so far? Okay. Very good. So now the question is of how to define non-invertible symmetries on the lattice. So a possible answer you might think is to just define them by a non-invertible operator D, which commutes with the Hamiltonian. However, if you define it in this way, it would not be clear how to impose locality on D. For example, if you consider sending O to D or D dagger, this action is not going to be locality preserving, even if O is the identity operator. So since this conjugation action is not a good action, and it's not clear how to define locality on D. So then the question arises of, which is that which non-invertible operators D qualify as non-invertible symmetries or as global symmetries? That's the question that we want to answer in this talk. So to answer that, let me first discuss an example which is a good non-invertible symmetry. And that's basically the simplest example of non-invertible symmetry, which is the Kramers-Vanier non-invertible symmetries on the lattice, which I assume many people are familiar with. So let's consider the Ising Hamiltonian. So we have a 1D chain of qubits. Z and X are Pauli matrices. So the critical Ising Hamiltonian, where the coefficient behind ZZ and X are equal, has a Kramers-Vanier symmetry, which transformation correspond to sending X to ZZ and sending ZZ to X. And then you could show that this transformation is actually implemented by a non-invertible symmetry operator D, whose explicit expression is given here for periodic chains of L sites, and is implemented in the sense that if you try to do a commutation relation between xj and d, x goes to zz and zz goes to x. So in the sense, D will generate this transformation. And it's non-invertible because DD dagger is not identity, but is 1 plus the Z2 operator. So defining the Kramers-Vannier symmetry by D, although is very concrete, but is not very satisfactory because it obscures the locality of this symmetry. And it's also very difficult to check whether a Hamiltonian commutes with this complicated non-invertible operator. However, checking whether a Hamiltonian is symmetric under this transformation is straightforward. Basically, you look at this Ising Hamiltonian, and with the naked eye, you just could check whether this Hamiltonian is symmetric under it or not. So then what we want to do, we want to define a symmetry by its transformation. But then the question is that what kind of local transformation are allowed? So this transformation that I discussed here is not a unitary transformation, but it's not clear what kind of transformation are allowed and what's the rule of the game. So the goal of the talk would be to define non-invertible symmetries by their action on local operators. So I will describe this action by a linear map phi from A to A, where A is the algebra of local operators. So then phi would be some non-invertible map, and it would be locality preserving, and it would satisfy additional condition that I will try to find and justify them. So importantly, we will argue that this additional condition guarantee the existence of symmetry operators and symmetry defects from phi. So from that sense, we would say these conditions are sufficient. And then I should say that this definition leads to a natural notion of non-invertible QCA. So if phi would satisfy this additional condition that I will discuss, I would just refer to it as a non-invertible QCA. And moreover, if this map preserves some Hamiltonian, you could call it a non-invertible symmetry of a Hamiltonian. So these two terms are kind of closely related, non-invertible symmetries and non-invertible QCA. And then at the end, I will discuss some index theory of these non-invertible QCAs, which is similar to index theory of ordinary invertible QCA. So that is the goal of the talk. Any question about the setup goal?
I have a quick clarifying question. Is your algebra
Yes.
of local operators going to be strictly I'm assuming they'll be strictly local and they won't be quasi-local, is that right?
Okay, that's a good question. So in this talk, I will not try to really discuss the issue with quasi-local operators. So as I would discuss, there would be two versions of this map phi. One version is that you look at each intervals and it will map it to a larger interval. So you only consider strictly local operators. Another version is just to take the C-star algebra in the infinite volume, and that would also include quasi-local operators. So one of the things which is, as I say, is work in progress is that, so for some of the step, we don't have an actual proof, and it's not, maybe it's not clear all the details, whether it's important to include them or not. But I believe there should be a version to say this condition in both cases, where you include them or do not.
Okay, thanks.
Thanks for the question. Any other question? So the most cleanest setup is just to consider A to be the algebra of all operators, even including those which are quasi-local. So A is just a single C-star algebra of the infinite chain. Okay.
But another quick question, I guess phi is allowed to have a kernel, right?
Say again, sorry, I didn't hear.
Is phi allowed to have a kernel?
Meaning mapping something to zero?
Yeah.
Yeah, definitely. So I'll discuss Kramers-Vannier, and Kramers-Vannier actually has a kernel.
Okay.
Thanks. Any other question? Okay. So, okay, the outline is that first I make the definition, then I will motivate this definition and discuss implication, and at the end I will discuss index theory and topological defects. Okay, so the motivation for this action on local operator is coming from quantum field theory. We know that in QFT, non-invertible symmetries correspond to non-invertible defects, and then a way to act on local operator and a local operator A is to take this topological defect, wrap it around the local operator A, and then shrink it all the way to the locus of A. And this will give you an action on local operator, which maps an operator A to a local operator as discussed here. And then it was pointed out in a series of very interesting works, and most importantly, series of work by Marshall Bischoff and collaborators, where they discuss this action in the context of conformal nets and to the rational CFTs, and they discuss that such map form a quantum channel. And then more recently, it was also discussed in the context. This quantum channel was also discussed in the context of lattice. So
Can
one
I
fact.
ask the question that I've asked you, but in this case, the quantum channel is preserving the probabilities, or it's trace preserving or not?
Yeah, I will discuss. I will discuss all of these things in a few slides.
Okay.
Yeah, thank you. I will discuss it. If I miss it, please ask me again. So before going to that detail of what do I mean actually by quantum channel, which I will describe very precisely, let me first make an important point, which is that this map phi is not globally well-defined on a circle. So it's well-defined on different patches, but on a circle is not well-defined. And the reason is the following, that if you're in a circle and you have two operators on, let's say here, on this side of the circle and this side of the circle, there are two ways to act. You could wrap a topological line from this side around it, or you could wrap a topological line around it from this side. And because on manifolds with different topologies, there is an ambiguity how you act on them, so this map would not be globally well-defined on a circle. I will discuss it in the case of Kramers-Vanier. So, however, I should also point out that if you want to have a globally well-defined quantum channel on a circle, there is a different map, which was discussed by this nice paper by Sakura and collaborators, and that map is well-defined, but you have to also include twisted sectors. So I would not focus on such a map because I want to act on local operators, and I want this map to be locality preserving, meaning mapping local operators to local operators. So this map would be different from this map constructed in this nice paper. And another trivial fact is that this phi, when is non-invertible, it doesn't act multiplicatively, meaning that phi of A1, A2 is not the same as phi of A1 times phi of A2. And you could see it by just doing this encircling action on local operators. So then you will get a tail, and this is not the same as phi of A1 times phi of A2. So let me discuss the Kramers-Vanier case more precisely. So what's the quantum channel in the case of Kramers-Vanier? So consider Kramers-Vanier on the lattice. As I said, let's assume that D maps X to ZZ and Z constructed such that D maps X to ZZ and ZZ to X. And the way it acts is that on Z2 even operator, so A plus is the algebra of Z2 symmetric local operators, it acts multiplicatively. And then it sends any operator which is Z2 odd to 0. So then from these three conditions and the fact that D is a linear map, this will define the action of D on any operator. Because any operator, you could write it as a sum of a Z2 even and Z2 odd one. The Z2 odd one maps to 0. And Z2 even operators, you just have to know them on a basis, which is X and ZZ. And then you use the multiplicative property to define the action on all Z2 even operators. So this is actually the Kramers-Vanier map. And as I said before, D is not globally well-defined on a circle because let's consider a chain, a periodic chain of L sites. And then let's discuss the action on Z1, ZL over 2. So you could write Z1, ZL over 2 as a product of ZZs on this side of the chain. Then it gives you a string of X's on this side. But you could also write Z1, ZL over 2 as a product of ZZs on the other side of the chain. And then it will tell you that this should be equal to a string of X's on the other side. So you see that there is no way to make this map to be globally well-defined on a circle. So however, it would be well-defined on an infinite chain, which would be the cleanest setup. So our setup is indeed to work with the infinite chain, on the infinite integer chain, where A is the algebra of local operators on the infinite chain. This would be all set up. Any question?
Sorry, one question. In the infinite chain, does the algebra of local operators for you include the truncated Z2 symmetry operator? a quantum
No, that
operator?
wouldn't be local operator.
I
No.
see. Okay. I see.
That's not a good operator if it goes all the way to infinity because they don't have a well-defined algebra. You cannot multiply them. Unless you pick some ground state, you go to its super selection sectors and you represent it by a bounded operator on some Hilbert space. Here, since we are discussing kinematics, we haven't fixed any states. There is no Hilbert space, so we cannot discuss those. We don't want to make any choice of states or super selection sectors. And without those choices, these operators don't form any well-defined algebra. So
I see.
the operators are strictly local, or they might have some decaying tails.
Okay, I see. So still, even in the infinite chain, you want to send all the Z2 operators to zero, right?
Yes.
Okay, good.
And this is compatible with this encircling action, right? Even in continuum field theory, if you consider Ising CFD and you wrap the Z2 odd operator, the Kramers-Wanier around the Z2 odd operator, you get zero, right?
Yeah, sure. Okay.
Okay. Thanks for the question. Any other question? All right. So then let me first tell you the rough definition of the symmetry that we want to propose. So we would say a non-invertible quantum stereo automata. First, it's a locality preserving quantum channel, and I will discuss what do I mean by that. The second condition is a notion of dualizability, meaning that if you consider the dual of phi, it should be also locality preserving quantum channel. And the third condition is purity, meaning that there is no non-trivial way to decompose and write this quantum channel as a positive sum of two other quantum channels. So this is just a rough description. Now I will go in details into each of these three definitions and motivate them. Okay, so the first one, as I said, is locality preserving quantum channel. So what's a quantum channel? So quantum channel, it's a unital completely positive map, and being locality preserving means that it has a finite range. So what's a UCP map? U means unital. It just means that this map, phi, maps identity to identity. So that's the unital condition. Positivity means that it maps a positive operator to positive operator. But complete positivity means that even if you tensor your system with some finite quantum dimensional system, then it also preserves locality. So it's kind of a stability condition. And algebraically, it corresponds to this equation for any choice of A and B. And the finite range condition or locality preserving, meaning that this map maps an operator supported on an interval I to a larger interval, to a L neighborhood of this interval. So given any finite interval I, if you act on the algebra supported on that interval, it maps to a slightly larger interval with size L. And it's important that this locality is only true for interval. For example, if you consider a disconnected regions, like some operator here and here, and you act on both of them, you don't only make each region larger, but you map it. You also get some operator in between the two regions. So locality preserving is only true for connected regions, such as interval in 1D. And since I'm working with infinite volume, let me also say that a state in the infinite volume is defined as a positive functional on the algebra of local operator to complex numbers. And the way that phi acts on states is by precomposition. So let's say you have a state psi, so you know the expectation value of any local operators on A. And the way you get state psi prime is to first act with the map phi on a local operator and then evaluate the expectation value of phi of A on your old state to get the new states. And indeed, quantum channel are the most general linear maps that you could consider on the set of normalized positive linear functionals. So unital is because you want to preserve probability and also send normalized states to normalized states. So indeed, as Sakura asked, to answer Sakura's question, we assume that they preserve probability. However, let me make one remark, is that R phi is a quantum channel in the Heisenberg picture because we are acting on local operators. So usually in finite volume, quantum channels are discussed in the Schrödinger picture where they act on density matrices. And therefore, they are represented by trace-preserving completely positive maps. Since we are working with the infinite volume, there is no preferred Hilbert space, and we cannot discuss density matrices. So we are forced to discuss quantum channel in the Heisenberg picture, where trace preserving is replaced by unitality. But yeah, the bottom line is that we do assume that these quantum channels preserve probability. Any question at this point? Okay. So let me motivate this. So as I said before, the motivation is by considering non-invertible symmetry in the continuum, where they do form some quantum channel. Let me also mention that invertible symmetries are special case of UCP maps because invertible symmetries correspond to star automorphisms, and they are all quantum channels or UCP maps. And Kramers-Vanier, indeed, it's a quantum channel because you could view it as a composition of two different UCP maps or quantum channel. So the idea is you first take a local operator and then project it down to Z2 even operator by doing this map, which is a UCP. And then this map is followed by this star automorphism defined on the algebra of Z2 even operators. Because it's a star automorphism is also UCP. So Kramers-Vanier indeed is a quantum channel. And what's an example which is not a UCP map? And these correspond to non-unitary but invertible transformations. For example, if you take a invertible operator U, the map that sends A to U inverse, it's a UCP map if and only if U is a unitary operator up to a C number. So in a sense, this UCP condition is kind of a unitarity condition on your system because it would forbid non-unitary invertible transformations. And as discussed before, is a notion of that it preserves probability. Okay. So this is our first condition, which was already discussed in this paper, that it's a locality preserving quantum channel. So now we have two additional conditions that we want to add. So the first one is the dualizability condition. So we want to say the dual of this quantum channel, which we denoted by phi star, must also be a locality preserving UCP map. So, but let me discuss how do we define this dual map. So our setting here is to work with a spin system. So we have a tensor product algebra, and where at each site we have a finite dimensional Hilbert space. So it's known that even though this algebra A is infinite dimensional, but there is a notion of tracing that you could define. So basically you could focus on n sites, and then there is a trace that you could define on n site because it's finite dimensional. If you normalize this trace such that the trace of identity is 1, then it turns out that this trace is well defined for the whole operator algebra, even though this operator algebra is infinite dimensional. And that's usually sometimes called the tracial state. And this trace, you could think of it as the infinite temperature states on this spin chain. So trace is something well defined. And then using this trace, you could define the dual UCP map phi star. And the dual is uniquely determined by this equation. So phi star is a unique map that for any local operators A and B, trace of phi AB equals to trace of A phi star B. So if phi star exists, it would be unique. So it's not an extra data. It's just determined by this equation. And let me also make a remark that a physical intuition of this tracial state should be viewed as a notion of a state of a UV state at the macroscopic level, that you should always assume that it exists. So in particular, to assume that it's dualizable, meaning phi star is a locality preserving UCP map, in particular, it will imply that phi must also be trace preserving. So phi is both unital and also trace preserving. So what's the motivation? You could say this might be an arbitrary condition. Why we are imposing this dualizability condition? And the one motivation is the following statement. You could show that phi is a symmetry of your Hamiltonian. If phi is a symmetry of your Hamiltonian, then phi star should also be a symmetry of your Hamiltonian. Meaning that So if phi is the symmetry of your Hamiltonian, it means that phi commutes with time evolution. Then with a simple line of algebra, you could show that if phi is the symmetry of H, then phi star should also be symmetry of your Hamiltonian. So then it would be bad to not impose locality preserving for phi star, because phi being a symmetry, phi star is also a symmetry, and it would be very bad that phi star doesn't have a symmetry. So that's basically the motivation that we are, one motivation that we are imposing this dualizability. Any question about this condition? So let me also mention that a Kramers-Vanier is indeed dualizable, because you could just construct its dual, and the dual of the Kramers-Vanier map is correspond to D composed with lattice translation. So this map D is a kind of a half lattice translation to the left, and its dual would correspond to half lattice translation to the right. So if you just work out the definition that I wrote in the previous slides, you will reach to this equation. And let me also mention that invertible symmetries are indeed dualizable, in the sense that if you take a star automorphism alpha, the dual of alpha would be the same as alpha inverse. And if alpha is locality preserving, you could show that alpha inverse should automatically be locality preserving. And I should say that this is true for tensor product algebras that we consider. But if you want to consider the alpha on a more general algebras, then the dualizability of alpha inverse would follow from alpha if you assume weak Hopf duality for that algebra. But for tensor product algebra, it's always there, so it's automatic. That's why people didn't have to impose it for alpha inverse. And what's an example of, and there is an example of a UCP map which is locality preserving, but its dual is not locality preserving. So this condition is non-trivial to impose. And a non-example is given by taking the Kramers-Vanier transformation in half of the space. So let me just show you quickly. So consider this quantum channel, which on negative sides acts trivially, but on positive sides acts as the Kramers-Vanier symmetry. So you could show that this is a quantum channel, and you could go and compute its dual, and you will find out that its dual is not locality preserving, in the sense that it acts Zj to a string of x0 to xj, and as you send j is larger and larger, this becomes more non-local and more. So it's a non-trivial condition to impose. And indeed, such a symmetry would be a very bad symmetry. If you want to find a Hamiltonian which has this symmetry, you will find out that this Hamiltonian should identically vanishes on the right half of the chain. So it would be very bad to impose these non-local symmetries. Sometimes they are very restrictive. They should not be thought as global symmetries.
Sorry, can I ask something? But isn't that supposed to be true for any symmetry operator, that the symmetry operator all in null space is not a symmetry, because it's not going to be topological, right?
Okay, so here I'm not ruling out Kramers-Vanier. So what I'm saying is that, let's say you didn't know it's coming from truncation of the Kramers-Vanier. So you just view dr as a global symmetry that acts on the whole chain. It just happens to be that on half of the chain it vanishes. It acts identically. I'm saying that this UCP map, its dual is not locality preserving, so it's not a good symmetry. The way that I construct this non-example is by truncating a Kramers-Vanier. I'm not making any point about Kramers-Vanier in particular. This is just how I construct this counterexample.
Okay, so you should also be able to construct a counterexample by truncating any other symmetry operator, even the Z2 symmetry operator.
Yeah. Or there might be a counterexample which is not correct. I might be also able to construct a counterexample which is not a truncation of any symmetry.
Sure. But I was just making the point that if you truncate any symmetry, if the symmetry acts non-trivially on the Hilbert space, the truncated symmetry operator shouldn't commute with the Hamiltonian. So
yes, but it not only doesn't commute with the Hamiltonian, but you cannot find any other nice Hamiltonian that it would commute with it.
Yeah, okay, I see.
Because this would not be the case for ordinary Z2 operator, right? If you take a Z2 operator and act on half of the chain, it still would be a nice symmetry, right? You could find many Hamiltonian that have this symmetry because it's locality preserving. It might not be the symmetry of the original Hamiltonian, but you might be able to find some other Hamiltonian.
I see. Okay, thank you.
Yeah, thanks for the question. So this is just to say that this condition is important to impose that the inverse is locality preserving. Any other question? Right. Okay, so now let's finally discuss the last condition, which is the purity. So this condition tells us that phi must be CP pure, meaning that it should be an extremal point in the convex space of all completely positive maps. Meaning that you shouldn't be able to write phi as a non-trivial combination of two other completely positive maps, phi1 and phi2. Meaning that if phi equals phi1 plus phi2, you could only write it unless phi1 equals phi1 and phi2 are proportional to phi itself for some t between 0 and 1. So it's important that t and 1 minus t are positive. This is the same as imposing that a state is pure. We would say that a quantum state is pure if you cannot write it as a convex sum of two other positive states. So what's the motivation behind this purity condition? One motivation is related to imposing that the symmetry is reducible, but a more important motivation is the following fact, that we could actually show that if phi1 plus phi2 is a symmetry of a Hamiltonian, then both phi1 and phi2 must individually be symmetries. If this hadn't been true, then it would be bad to impose purity, because it could be that phi1 and phi2 are not symmetries, but their combination is the interesting of the symmetry of your system. So then we would lose some interesting symmetries by imposing purity. But because we have this statement, then without loss of generality, we can just focus on CP pure maps, because these are the building block symmetries of our system. And I should say that alternatively, you could view this requirement as saying that if you have a non-invertible QCA phi, which is locality preserving, if you decompose it into the sum of two CP maps, you should also impose that each individual CP components are locality preserving. So I will discuss, this is not always automatic. There would be an example of a locality preserving quantum channel, which is locality preserving, but once you write it, decompose it as a sum of two other channels, then these sub-channels would not be locality preserving. So it would be important to impose this condition. But in our setup, we just focus on CP pure maps. So as I said, the motivation is coming from this statement that if phi1 plus phi2 is a symmetry, then phi1 and phi2 individually should be symmetries. So in the next couple of slides, I will do a short detour and try to give some backgrounds and tell you how we can actually prove this statement. That if phi1 plus phi2 is a symmetry, then they should be both symmetries. So then we have to introduce some notions from system.
I have a question. For topological defects, as you know, we have a concept of preferred normalization. Here, it seems that for phi, there is no such a concept because you can rescale phi. Is this true?
So here, good question. So first here, I'm assuming that is unital. So I'm using some normalization. But what you mean is that the normalization in the continuum is different because you act identity to the quantum dimension of phi. Right?
Yeah.
So indeed, as I will discuss at the end, there is a way to define the quantum dimension of phi. Then you could multiply phi by its quantum dimension such that it would map identity to the quantum dimension. And if you use that normalization, then probably we can show that once you compose these maps, the fusion coefficient would be integral.
I see. Okay.
A theorem such as that is proven by a nice paper by Nat, Shia, and collaborators that I will discuss. That I will mention.
But so the statement that you have here in the first three lines is not a complete statement, right? Because it cannot be valid for any t.
What cannot be valid for any t?
Well, you cannot have that both phi and T phi are good symmetries for any T.
So the way here we define symmetries, the normalization is not very important, right? So because if we have a map phi, we just call it a symmetry if it preserves the Hamiltonian in this sense. So there is a generalized notion of what do we mean by a map to preserve the Hamiltonian.
Okay. So here you're not paying attention to the
Yeah, I'm not
normalization.
paying attention to that.
Okay,
If you want to
okay.
discuss fusion coefficient might be important, but here I'm not, yeah, I don't care.
I see. Okay, thank you.
Thanks. So for phi, for simplicity, I assume is unital, but for phi 1 and phi 2, I'm proving something more general that you cannot write it as any kind of combination. Yeah. And I
So
should
can I
say,
ask a question?
yes,
Can I think of this condition as like the counterpart of simple objects and fusion category symmetries?
yes. This is indeed the same as the simplicity condition, the irreducibility. Yeah. Thanks for the question. But the motivation is, so that's one motivation, but the other motivation is this statement. That's a kind of a physical. So that motivation is if we want to land on fusion categories, but this condition tells you that even if we don't know that we want to discover fusion categories, this is a physical condition to impose. Okay. So let me take this detour to explain this relation. So one important fact about this UCP maps or quantum channel is this notion of multiplicative domain that I will discuss. We'll discuss in this old paper by Choi. So one important tool is this Cadison-Schwarz inequality that is true for any unital completely positive map. That if you take A, any local operators, phi of A dagger A is greater or equal than phi of A dagger and A. And what is more important is that an equality happens if and only if this equation is true for any x. So if it's true for x equals A dagger, then it's true for any other x. So it's kind of a multiplicativeness. So motivated by this, then Choi defines this multiplicative domain of any quantum channel or UCP map, and it corresponds to this particular subalgebra. So you look at all local operators such that phi of A dagger A is phi of A dagger times A, and phi of A dagger equals to phi of A times phi of A dagger. This is a nice subalgebra. And because of this statement, this subalgebra has a nice property that the phi acts multiplicatively on it, meaning the phi of AX equals phi of A times X. Is not true only for x's inside A of phi, but is indeed true for any other x's. So it's not only multiplicative within the subalgebra, it's also multiplicative if you bring an element from outside the algebra and multiply it from element inside the algebra. So it's a very important concept, the multiplicative domain of a map, that here I define it by A of phi. So for the Kramers-Vanier, the multiplicative domain of Kramers-Vanier is the algebra of Z2 even operators, as we see earlier, that on the Z2 even operators act multiplicatively. And more generally, there is this nice connection with the continuum QFT or from the operator perspective on non-invertible symmetries. So let's take L to be the symmetry operator associated with this non-invertible QCA phi. Then the picture is that A is inside the multiplicative domain of phi if and only if A has this nice commutation relation with the symmetry operator L. Meaning that if you try to push the non-invertible symmetry operator past through the local operators, we know that for non-invertible symmetry, we usually should get some tail attached to this local operator. But if this tail is not there and L has a nice action on A, then LA just becomes another local operator times L. And we know that is true for Z2 even operator in the case of Kramers-Vanier. But the nice fact is that having the non-invertible symmetry having a nice action on some set of local operators has a purely algebraic characterization via this multiplicative domain that we could define here. So you could think of multiplicative domain as a set of all local operators where phi has a nice action in this sense. And another point is that these UCP maps actually act invertibly on their multiplicative domains. And the inverse is given by the dual map phi star. And moreover, you could show that A is inside the multiplicative domain if and only if phi star phi of A equals A. And this just follows from a couple of lines of algebras, and it only assumes the trace preserving condition. So this condition is true for any unital and trace preserving completely positive maps. And we know from continuum picture that is also true. Okay, so now, after knowing this concept, we are ready to show this statement that if T phi 1 plus 1 minus T phi 2 is a symmetry, then phi 1 and phi 2 should be individual symmetries. So basically, to show that, we have to show that if this combination preserve a local operator A, then both phi 1 and phi 2 should preserve a local operator A. So this follows from two statements. One is that one statement that we need is that if phi of A equals A, meaning that if phi preserve A, then A should be inside the multiplicative domain. So it means that if the encircling action preserve A, then A should commute with the topological defect. And the second statement is an important theorem of Choi on the same paper, which characterizes the multiplicative domain of composite quantum channel. So if you write phi as a convex combination of two UCP maps, it was shown that the multiplicative domain of phi equals to the intersection of the multiplicative domain of phi 1 and phi 2 intersected with the subalgebra where all three maps agree with each other. So now using these two, it's easy to show that, because if this combination preserve A, from this statement, we know that A should be inside the multiplicative domain. Then using Choi's theorem, we know that phi 1 and phi 2 should agree with phi on the multiplicative domain. And because we assume that phi preserves A, so then phi 1 and phi 2 should also preserve A. And the proof of the statement 1 is also easy. And let me not discuss it, but it's basically just follows from the trace preserving condition and some positivity argument. Basically, so yeah, what we have to show to say that A is inside the multiplicative domain, we have to show this equality. But because the difference between them is a positive operator, it only suffices to use it after taking the trace. But then this would follow because of the trace preserving property of the phi. So there are some implication of this kind of facts about the multiplicative domain, which are quite interesting. So let me just, before continue, let me discuss this implication. So one implication is that you could discuss gauging in a purely algebraic way. So you could say that gauging a non-invertible symmetries generated by a set of non-invertible QCAs, phi I, correspond to another non-invertible QCA, G, from your operator algebra A to another operator algebra of, let's say, the gauge theory, such that it satisfies the following property, that G star G is a convex combination of your non-invertible symmetry. So we claim that this is the most general characterization of gauging in this formulation. So I should say, from what I said before, and Choi's theorem, it follows that the multiplicative domain of G is the same as the intersection of the fixed point of all these phi's. So this would mean that the gauging map G acts invertibly on Hamiltonian symmetric under phi I. Meaning that if you take a Hamiltonian H which has symmetries phi I, then applying G, you will get the Hamiltonian of the gauge theory. So this is the gauging map. But then you could gauge another symmetry in the gauge theory to go back to your Hamiltonian H. And the gauging back procedure is given by G star. So one implication is that, let's say such an equality, you have such an equality for some set of phi I and G. Then from what I said, physically you could say this would mean that these maps phi I are gaugeable. And therefore, because they are gaugeable, they cannot mix with lattice translation. So that's a strong condition. So this is only a physical condition, but you could actually try to make it into a rigorous statement. So let's assume that this equation is true, but anyway, phi I mixed with lattice translation. So if phi I mixed with lattice translation, it would mean that its fixed point algebra is trivial. Because if you have a translation like symmetry, it cannot have any fixed point. But if the fixed point of one of the phi's is trivial, because of this statement, it would mean that the multiplicative domain of G is trivial. So it means that G does not act invertibly on any local operator. And one of our conjecture is that such a thing should be forbidden. So from the purity condition and locality preserving condition, we conjecture that the multiplicative domain should be a very large subalgebra. Particularly, it should have a trivial commutant. We haven't been able to show it, but we believe that this is true, that this should follow from the purity condition. So then we believe that there should be a way to prove that if such a phi I appear on the right-hand side, it would be impossible for them to mix with lattice translation. And this would have some more interesting consequence. So if phi I don't mix with lattice translation, and they should form some kind of a fusion category. And from the classification, we know that it means that phi I, they should have integer quantum dimension because we are in a tensor product Hilbert space. So that would mean that the quantum dimension of G should be a square root of an integer because the quantum dimension square would be a sum of integers. And that would imply this weakly integral conjecture, which was discussed before and also by talk with Kansei a couple of weeks ago and this nice paper by Kansei. I should say that Kansei also had an argument for this weakly integral conjecture, but his argument was a different thing. So he was relying on the fact that if you impose two symmetries and you look at the GNVW index of all the channels should be the same. So I will discuss the GNVW index at the end of the talk if I have time. But that it's also possible that that conjecture would also follow from this choice theorem. But okay, we go on.
I want
Any
to ask a
questions?
question about the last part. Is the statement that if the symmetry is gaugeable, if the non-invertible symmetry is gaugeable, then it must be weakly integral?
So I'm only saying that every element that appear on the right-hand side of such equations, they should have integer quantum dimension. And that was the physical argument why they should have they should have integer quantum dimension. So it's not the same as saying what you said. It basically means that given any realization, if you take any element, you multiply it by its dagger or its conjugate, the elements that appear on the right-hand side, they should be gaugeable in this sense. So they should not mix with lattice translation.
I see. So, but this G is not really a QC acting on a fixed algebra. It's mapping from A to another algebra. So in what sense?
Yeah, but in particular, it could also be a map from A to A. You could also apply it when it's mapped from A to A.
I see.
Okay, thanks for the
And
question.
in that case, and also assume that G form a fusion category, then it must be weakly integral. That's the statement.
Yeah.
Okay, sorry.
Any other question? Okay, let me actually go on. Let me go over it fast. I feel that I'm out of time. Okay.
Don't worry about the time.
Okay, nice.
I'm not opening the floodgate, but you can take your time.
Okay, thank you. Good. So, okay, now let me discuss that the Kramers-Vanier symmetry is also satisfy our condition of purity. So I want to show that the Kramers-Vanier map D is pure in the sense that if D equals TD prime plus 1 minus TD double prime, then we need to show that all these three maps should be the same. So the proof is kind of a simple proof. So first, let's invoke the choice theorem, which tells us that the multiplicative domain of D should be the intersection of the multiplicative domain of D prime and D double prime with the subalgebra where all the three maps agree with each other. So then the multiplicative domain of D corresponds to Z2 even operator. So then it will imply that D prime and D double prime agree with D on all Z2 even operators. So then to show that D prime equals D, we just note we just need to show that they agree on a single Z2 odd operator, such as Z0. Then we use the multiplicative property to say that they should agree on all operators. So we just have to show it for one point. Let's say Z0. We just have to show that D prime of Z0 is 0. So to do that, let's consider this anti-commutation relation. So we know that the string of X anti-commute with Z0. Let's take D prime on both sides and use the multiplicative property to get to this line. And we know that this is a Z2 even operator, so the action of D prime should agree with the action of D. So this becomes just Z minus NZN. So it would be implied that D prime of Z0 should anti-commute with this operator. But D prime of Z0 is some operator supported near site 0. But this equation should be true for any n, and we could take n to be large enough such that its support don't touch the support of D prime. So then it should commute with this operator. So then such an equation would be impossible unless D prime of Z0 equals to 0. And because of that, we know that D of Z0 is also 0. So we have shown that if such a thing is true, D prime equals D double prime equals D, which means that D should be actually a pure map. There is also another proof, but it's used as another techniques. But anyway, this is some proof that can be easily raised here. But Kramers-Mann is indeed pure. Let me also mention that using choice theorem, it would be very easy to show that all invertible symmetries are also pure. And again, the idea is the same thing. Because the multiplicative domain of an invertible symmetry is the whole algebra, it will imply that the component should agree with D on the whole algebra. So it's just the obvious consequence of choice theorem. Finally, let me discuss why this condition is important. Because there are some non-examples. So a non-example that is both locality preserving and dualizable, but is not pure, is coming again from truncation of some symmetry. In this case, it's coming from truncation of lattice translation. So let's consider alpha, which acts trivially on the left half of the chain on all the negative sides, but moves all the positive sides one side to the right. If we consider such a map, and this would be also dual, so its dual is also locality preserving, this alpha would not be pure because you could decompose A of alpha as these two projections. So note that site 0 doesn't appear in the image. So you are free to use this projection to decompose it as a sum of two completely positive maps. And indeed, these CP components are not locality preserving because they are not unital. A map, if it's locality preserving, should be unital. But because these two sub-channels are not unital, they are not locality preserving. So it means that alpha is not a good symmetry. We don't want to consider alpha as a symmetry because it would imply that its subcomponent is also a symmetry, but this is not locality preserving. And indeed, alpha is not a good symmetry because a Hamiltonian symmetric under alpha must vanish identically on half of the chain. Okay, any question before going to the other topic? Okay, so finally, let me discuss the index theory of this non-invertible QCA. So to discuss the index theory, we have to discuss this notion of blend equivalence that is usually discussed for ordinary invertible symmetries and is also important in some anomaly analysis that have been exploited recently. So we would say that two non-invertible QCAs, phi1 and phi2, are blend equivalent if there exists another non-invertible QCA, phi1, 2, such that phi1, 2 agrees with phi1 on the left half of the chain, and it agrees with phi2 on right half of the chain. And we also allow some small corridor L where we don't make any statement about phi2. So we just have to know that on the very left, it agrees with phi1, and on the very right, it agrees with phi2 for some location of J. So the blend equivalence classes of invertible symmetries in 1 plus 1D are determined by a single invariant, which is known as the GNVW index, which is some positive rational numbers. So this index basically captures the amount of mixing of symmetries with lattice translation, how much information is transformed to the right or left. So what we will do, we would generalize this GNVW index for this non-invertible QCA, we would argue that for non-invertible QCA, this index is still well defined, given that the QCA satisfy all our three conditions. And then we conjecture that the GNVW index and a new index that we will discuss, which captures the quantum dimensions of these maps, are complete invariants of non-invertible QCAs in 1+1 dimension up to blend. So this would be our conjecture. So as we will explain, to establish this conjecture, it suffices to show that non-invertible QCA admit a topological defect or sequential circuit presentation. So that's the only thing that is work in progress and we haven't been able to show. If we can show that non-invertible QCA admit a topological defect or sequential circuit presentation, then the index theory follows, as I will explain. So let me discuss what do we mean by topological defect. So a topological defect corresponds to two data. The first data is a local modification of your operator algebra. So inserting a defect on the link JJ plus 1 amounts to changing the operator algebra near the vicinity of this link. So basically, from all the sites to the right, we just use the ordinary algebra. So this is operator algebras of sites greater than J. And for greater than J minus L is also the same, but we only modified around this site. Okay, so it's still a tensor product algebra. It's only modified around this link. Another condition is the topologicalness condition, which means that these modifications can be moved via local unitary transformation, meaning that there is a automorphism, a lambda JD, that maps this defect algebra to this defect algebra. And it's important that this unitary transformation acts identically away from the defect. It has only supported on the vicinity of this site. So that's what we mean by topological defects. Should say this is independent of the Hamiltonian, but if you have a Hamiltonian, there is a nice description of it. So this algebra B is a very important algebra here. We refer to it as the boundary algebra. So it's a subalgebra of the physical sites from site J minus L to J. It might also include some additional ancillary sites. Let's say you add n qubits or n degrees of freedom. So this boundary algebra characterizes the defect degrees of freedom and is quantified by a single number, which we refer to it as the lattice quantum dimension, which is the ratio of the dimension of this algebra by the dimension of the physical site. It's also a positive rational number. So it characterizes defect degrees of freedom. For example, for lattice translation correspond to adding a qubit in one direction, another direction is corresponding to removing a site. So the most general thing is to add some number of degrees of freedom and project out some number of degrees of freedom. So any question about this definition? Good. So now given this data of the defect, it leads to a defect creation sequential circuit. So let me describe what do I mean by that. So you could take a formal infinite product of these local unitary transformation, all the way from minus infinity to some site J. So although this is an infinite product, its action on local operator is actually well defined. Because if you take a local operator, which is local, only finitely many terms gonna act on it. So it will give you a well-defined map from your ordinary operator algebra to the defect operator algebra. So that's why we refer to it as a defect creation sequential circuit. So there are two of them. You could act with lambda, bring a defect from minus infinity to some site J, or you could bring a defect from plus infinity by using a lambda inverse to this site. So we call it defect creation sequential circuit because if you act with this sequential circuit on the untwisted Hamiltonian, you will generate the defect Hamiltonian. And the statement that the Hamiltonian is symmetric, it means it doesn't matter if you bring the defect from minus infinity or plus infinity. So this is a statement of the Hamiltonian being symmetric. You could show that. Another important fact is that given this sequential circuit, there is a way to construct a quantum channel. And to our knowledge, such an equation hasn't appeared before. So there is a very concrete way to take this sequential circuit and construct a UCP map. The idea is that you first bring a defect from minus infinity to link JJ plus 1, and then you use the dual of this defect creation sequential circuit, which we call it the defect annihilation circuit, to annihilate this defect. And at the end of the day, we get a map from A to A without any defect algebras. And let me also point out that this dual is not the same as the inverse. Although this is a product of local unitaries, but is only a formal product of local unitaries. If you take its dual or its star, it would not be the same as the inverse. So in particular, this map could have a kernel and it's non-invertible. So it's another, it's a UCP map. This is invertible, but this is not invertible. And as a result, this phi would be not invertible. So one important fact is that a sequential circuit presentation of phi, it would imply that is locality preserving from the left, meaning that if you act on an interval from J1 to J2, it cannot map it to something which is very to the left of it. So it kind of guarantees localizability from one direction. So localizability of phi from left and localizability of phi star from the right. So it means that we're on the right track. And finally, we would say a non-invertible QCA has a sequential circuit presentation if there exists a pair of dual defects D and D bar, such that you could generate phi from moving D from left to right, and also generate phi from moving D bar from right to left, which correspond to these two equations. So then the sequential circuit presentation in this sense would guarantee that phi is both locality preserving and is also dualizable. So that would mean that the two conditions of localizability and dualizability are actually necessary if we want our symmetries to admit a topological defect interpretation. And I should say also that the purity condition corresponds to the irreducibility of the defect, in the sense that the image of this defect creation sequential circuit should have a trivial commutant. And let me also point out that there is also this nice paper by Nat, Liu, and Xie Chen, that they use a different kind of definition of generalized symmetries. So they don't impose locality, and they would call an MPO, a non-invertible symmetry, if they admit a sequential circuit, but only from one direction. So they only impose the existence of D, a sequential circuit either from left to right or right from the left. The difference of what we are doing is that we want to impose that there exists two different sequential circuits, one from left to right and one from right to left. And if you have both, then it would guarantee the dualizability and locality preserving condition. So finally, let me discuss the index theory. So given a sequential circuit presentation of a non-invertible QCA, phi, then there is this lattice quantum dimension, which corresponds to the lattice quantum dimension of the defect and the dual defect, that I defined them by D left and dr, similar to what Kansei did. And then the statement is that this DL and dr captures our complete invariance for the blend equivalence of this QCA. This is because if given two pairs of sequential circuit with the same quantum dimension, there is an explicit construction of a blend between them. So it means that these are complete invariants. And from these two invariants, we could define the quantum dimension and the GNVW index. Quantum dimension is the square root of D left times D right, and the GNVW index is the square root of the ratio. So for Kramers-Vanier, there is a defect construction. So the defect opera algebra is the same as the untwisted algebra, but for the dual defect, it corresponds to adding a single qubit. And these are the gates that you could construct a sequential circuit with it, which we discussed in the paper with Nati and Shuheng. And so you see for Kramers-Vanier, D left equals 1 and dr equals 2, which means that both the quantum dimension and the GNVW index should be equal to root 2. So let me escape these slides and go to the summary. So as a summary, we propose an upper algebraic definition of non-invertible symmetries on the lattice and non-invertible QCA. This allows us to discuss the blend equivalence between this non-invertible QCA, which is actually different from the circuit equivalence, which is discussed in the invertible symmetry case. For invertible symmetries, circuit equivalence and blend equivalence are the same, but this is it's not true for non-invertible QCAs. And then, so our definition of non-invertible symmetries allows us to discuss them directly in the thermodynamic limits, and we hope that this will have some application to discuss some rigorous anomaly analysis of non-invertible symmetries and maybe derive some LSM type theorem. So let me thank you. Attention.
Great, thanks very much. It was a nice talk. Can I start with a question? Could you go back to
Yes.
page 16, please? It's about these gaugeability conditions.
Okay.
Could you repeat again what the exact statements about the gaugeability versus the integrality or weaker
Okay, good.
integrality?
Yeah, maybe it was not clear. So let me start. So let's assume that there is a set of non-invertible QCA, phi I and G, and they satisfy this equation.
Mhm.
So I want to argue that if you have such an equation, then phi I cannot mix with lattice translation. That's the claim. So let me give you one physical argument or maybe hint, and then something more mathematical. So the physical argument is that if phi I appears on the right-hand side of G star G, you could interpret this by saying that this combination on the right-hand side has a structure of a Frobenius algebra. So it means that it's kind of a gaugeable algebra.
Mhm.
But we know that if a symmetry mixed with translation, it shouldn't be gaugeable. It should be impossible. So that's kind of a hint of why phi cannot mix with translation.
Okay.
A more mathematical way to describe it is that if phi mixed with lattice translation, its fixed point algebra should be trivial.
Right.
So then it would imply by the choice theorem that the multiplicative domain of G should be trivial.
I see.
And we believe that this should be impossible given our free condition. But we haven't been able to mathematically show that.
Okay, great. Thank you. Any other questions? I have another question. So you always give the example of Kramer-Zwani. Have you considered other setups?
Yeah, good question. Yeah, so we have many other examples. For the sake of time, I didn't have the time to discuss it.
Yes.
One important examples, which in many aspects is different from Kramer-Zwani, is the cosine symmetry.
Mm-hmm.
Particularly when the rational
automorphism. Yes.
Yeah, so for Kramer-Zwani, for the cosine symmetry, it wouldn't mix with translation, so the GNVW index is trivial, but it has quantum dimension 2.
Mm-hmm.
And it also get all of this property, you could show it for the cosine symmetry. So I didn't have time to discuss it. Yeah.
Any other questions? We had lots of questions already, but I don't see anyone else. So let's thank Sahan again. I'll stop the recording and